Good morning, everyone. I'm Darshini Mahendran. Today, I'm here to present my paper, Extracting Adverse Drug Events from Clinical Notes. This is the outline of today's presentation. What is adverse drug events? Adverse drug events, AD in short, are unexpected incidents or accidents related to the administration of a drug and its attributes. This can include overdoses, allergic reactions, drug interactions, and medication errors. Conditions caused by undiscovered ADEs can increase the cost and risk and impact the patient economically and mentally. This can be prevented if we identify the potential reason and the information regarding the drug on time. Identifying ADEs require information not just about the drug itself, but the attributes describing the drug and why the drug was initially being taken. But processing such information manually from the clinical text is challenging due to the complexity of language and domain-specific knowledge involved. Next, we'll take a look at the data set. In this work, we evaluate our approaches on the National NLP Clinical Changes N2C2 2018 AD dataset. This dataset contains AD mentions, drug-related attributes, and drug-related relations from patient discharge summaries. The right side of the table shows the relation types and the statistics of the N2C2 dataset. And left side shows an example of a sentence that includes an AD entity, a drug, and its attribute of the drug. Next, let's move into the methodology. In this work, we utilize rule-based, deep learning, and BERT-based approaches. We'll look into each approach in detail next. The rule-based approach. Our rule-based approach decides whether a relation exists between two entities utilizing the co-location information between them. In other words, it depends on how the word is co-located with other words within the sentence. We use a graph-based traversal algorithm to find the selected entity's closest occurrence on either side of the other entity. For each entity, we traverse both sides until the selected entity's closest occurrence is found. So we explored the following traversal mechanisms. Then we report the best traversal mechanism in our results, which is the left side only traversal and the left first and then right traversal. Now let's see how the left only traversal works. The figure here shows an example of a sentence from the data set. The sentence, doctor prescribed Zofran 8 mg and lorazepam 0.5 mg for nausea. This contains a strength entity 8 mg and two drugs, Zofran and lorazepam. But the strength entity 8 mg has a relation with the closest drug, Zofran, but not with the drug, lorazepam. And this is captured correctly during the left-only traversal. Also, we conducted the traversals in two modes, bounded and unbounded. In the bounded, we limit the traversal to only a single relation per relation class, and in the unbound, we allow an entity to be linked to multiple other entity classes with the same relation. Next, we'll move to the deep learning based approach. Here we utilize convolutional neural networks, CNN. The approach here includes two CNN architectures, sentence CNN and segment CNN. Sentence CNN. This diagram summarizes the implementation of a sentence CNN. The sentence CNN learns the representation of an entire sentence at once and predicts the label. First, it extracts the sentence where the entities are located. For example, if we take the sentence, I took aspirin for my headache yesterday, the sentence is tokenized and each word is represented by a vector using word appendix. This gives us a sentence metric, which is then fed into the convolutional units. In this example, we consider a filter of size 3, and the convolution layer runs the features, and the max pooling layer extracts the most important feature from the entire sentence. Output is then flattened and sent through the dense layers. Finally, the softmax layer outputs the probabilities of each target classes, which is then converted into one-hot encoded vector. The classification error is then backpropagated and the model is retrained until the error is minimized. Next CNN model is segment CNN. In segment CNN architecture, we saw each relation is represented by the entire sentence. But different segments of the sentence can play different roles in deciding the relation class. Therefore, here we divide the sentence into segments based on the position of the entities in the sentence, as shown in the example here. Based on where the entities are located in the sentence, we divide the sentence into following 5 segments: preceding, entity 1, middle, entity 2, and succeeding segments. This figure here shows an abstract view of the construction of the segment CNN. For example, in this sentence, I took aspirin for my migraine headache yesterday afternoon. Aspirin and the migraine headache are the entities. Each of these segments are then fed into separate convolutional units, and each convolution unit applies a sliding window that processes the segment and feeds the output to the max pooling layer to extract important features. The difference here is the output of the max pooling layer of each segments are concatenated before passed into the dense layer, as shown here. So finally, the output is converted into one-hot encoded vector. We'll move to the next approach, BERT, bidirectional encoder representations from transformers. In 2018, Google introduced BERT. BERT embeddings are contextualized word embeddings that incorporate the context in which a word is currently being used into representation. A context-based representation of a token is generated based on the surrounding words in the text. Following are the pre-trained BERT models we used in our approach. BERT cased and uncased are the general BERT models trained on a large corpus of English data, book corpus and Wikipedia. BioBERT, this model is initialized with the general BERT, further trained over the corpus of biomedical research articles from PubMed abstracts. Clinical BERT initialized with BioBERT and further fine-tuned over the Mimic3 clinical node corpus. Our approach uses BERT contextualized embeddings and feeds the output into a simple neural network. We first break the sentence into tokens, as shown here, and then pass it through the pre-trained BERT model. Inside BERT, they are further tokenized into subwords, and the output vector representation is fed into a fully connected dense layer for classification. These are the evaluation matrix we use to evaluate our approaches: precision, recall, and F1 score. We report micro averages for the system performance. Now let's move to the results. The table here shows the results of our rule-based approach on N2C2 2018 dataset for the top 3 traversal mechanisms we described before. So here we can see the left-only traversal performed well overall for all relations except ADE drug and recent drug, which performed well with the left-right unbounded traversal. The key takeaway here is the co-location information is sufficient to identify most relations. We treat this approach as our hard baseline. The results of the 2 deep learning based approach are shown here, segment CNN and CNN CNN. The results show both models performed comparatively similar. In theory, we believe that segment CNN should have performed better. But in this work, we treat ADE extraction as a binary classification problem and build a separate model for each relation type. We believe this is due to this, for both models, we get similar results. So this table here shows the results of 4 BERT models we discussed before. We can see an overall improvement in the results with this approach compared to the previous approaches. Some BERT models perform better in some classes, but overall, if we take a look at the system performance, we can see the all four BERT models performed similar. In this table, we present the results of each of our three approaches. From the results, we can see the overall, the BERT-based model outperformed the other two approaches except for the strength drug and the frequency drug and form drug, which did good with the rule-based approach. Also, for the entity drug pairs that perform poorly with other approaches, such as AD drug, recent drug, and duration drug, performed well with BERT approach. We can see a higher precision and recall for almost all categories. When comparing the rule-based to the deep learning-based approach, the rule-based obtained a higher overall precision and recall and F1 score, except for the relation heady drug and recent drug. Here we compare our BERT results with two previous works, Wei and Alamova. This table shows the F1 scores achieved by each model. The F1 scores of all three models of Alamova are lower than ours. The F1 scores of Wei's and ours are almost same, but we find the results complementary because the relations that did not perform well with Wei's model performed well with our model and vice versa. So we believe this is due to the three differences between our systems. Wei represent entity drug pair in an input sentence using the semantic type of the entity to replace the entity itself, whereas we don't do any such replacement. And Wei perform a multi-class classification, whereas we perform a binary classification, creating a separate model for each entity. And for clinical BERT, Wei fine-tuned the general BERT over mimic3, while we fine-tune the bio-BERT over mimic3 for. Let's look at the conclusions. We explored a rule-based, deep learning-based, and contextualized model, contextualized language model approaches for AD extraction. BERT-based approach outperformed other models overall and obtained the state-of-the-art performance. However, from the rule-based results, it's safe to say co-location information is sufficient to identify most of the relations, as the rule-based approach obtain a higher precision and recall for certain relations. For example, strength drug, form drug, and frequency drug. Thank you, everyone. Questions?